Hey everyone, and welcome. Today, we're going to tear down one of the absolute cornerstones of modern system architecture, the load balancer. Seriously, if you're building any application you hope will take off, understanding this piece of the puzzle is completely non-negotiable. So let's jump right in.
So, picture this. You've just launched your brand new app. It's awesome, it's getting some good buzz, and then, boom, it goes viral. Like overnight, the traffic just explodes. What happens next?
Well, here's the harsh reality. A single server is gonna get crushed. It just can't handle that kind of fire hose of requests. Pretty soon, things start to time out. Your app slows to a crawl. And that amazing user experience you spent months designing, yeah, it's completely gone. You've basically created a digital traffic jam, and your big moment is turning into a total disaster.
But don't worry, there's a hero in this story. To fix this mess, we need to bring in the traffic cop of the internet. And this, right here, is where the real magic of scalability begins.
A load balancer. I mean, the name says it all, right? It literally balances the load. It sits out in front of all your servers, and its only job is to act as this super intelligent traffic cop, directing all the incoming requests so that no single server gets buried in work. So why do we use one? Well, it really comes down to four key benefits, or pillars. First, and this is the big one, scalability. As your traffic grows, you just add more servers to the pool. Easy. Second, availability. If one of your servers suddenly dies, no problem. The load balancer just stops sending traffic there. Your app stays online. Third, performance. Users get a way faster, snappier experience because requests are always sent to a healthy, responsive server. And finally, security. Your actual servers are hidden from the outside world, tucked away safely behind the load balancer.
Let's actually follow a request from start to finish. So a user types in your website. The first thing that happens is DNS, the internet's phone book, points them not to one of your servers, but directly to the load balancer. The load balancer grabs that request, looks at his pool of servers, and uses a special algorithm to pick the best one for the job. It forwards the request, the server does its work and responds back to the load balancer, which then passes that final response back to the user. And the craziest part? This whole complex dance happens in milliseconds, and the user has absolutely no idea it's even going on.
So, how does it know which servers are best or healthy? That's where this crucial feature called health checks comes in. The load balancer is constantly poking each server, asking, hey, you alive? You doing okay? If the server responds correctly, it's marked as healthy. If it fails to respond or sends back an error, it's immediately marked as unhealthy and taken out of the rotation. This is the secret sauce to high availability.
All right, so now that we know what it is and why we desperately need one, let's get into the how. How does it actually decide where to send the traffic? It's not just random. It follows a specific playbook of different strategies or algorithms to do its job. The first category is what we call static algorithms. You can think of these as simple, pre-configured rules. They're not looking at what's happening on the servers in real time. They're just following a script you gave them ahead of time.
The most basic strategy of all is called round robin. It's super simple. The first request goes to server 1, the second to server 2, the third to server 3, and then it just loops right back to server 1. The good thing? It's easy to understand and predictable. The big downside? It assumes every server is identical. It doesn't care if one server is a supercomputer and another is, a 10-year-old laptop. Now, there is a variation called weighted round robin that lets you tell it, hey, this server is twice as powerful, so send it twice the traffic. Next up in the static playbook is IP hash. This one is pretty clever. It takes the user's IP address, runs it through a mathematical function to create a unique hash, and then uses that hash to pick a server. The result? That user will always be sent to the exact same server every single time they make a request. This is really useful for something called session stickiness, which we're definitely going to talk more about later. The potential problem, though, is if a bunch of users from the same company network all hit your site at once, they could all get sent to the same server and overload it.
Okay, that brings us to the much smarter category, dynamic algorithms. Unlike the static ones, these are intelligent. They actually check on the real-time state of the servers, like how busy they are or how fast they're responding, before they make a decision.
Probably the most popular dynamic method is least connection. And the logic here is it's elegant. The load balancer simply checks which server has the fewest active connections right now and sends the new request there. It's a fantastic way to distribute the work based on how busy each server actually is. Its one little flaw is that it assumes every connection takes the same amount of effort, which, as we know, isn't always true.
For an even more user-focused approach, there's the response time method. The load balancer constantly measures how quickly each server is responding to requests, on average, and it sends the next request to whichever server is currently the fastest. This is awesome because it directly optimizes for the one thing your user actually cares about: speed. And the really advanced load balancers can even check things like the actual CPU and memory usage on each server to make even smarter decisions.
Okay, let's level up for a sec. What we're about to talk about, Layer 4 versus Layer 7, is a classic topic. This is the kind of stuff that for sure comes up in senior engineering interviews, because it really gets to the heart of how a load balancer sees the traffic it's handling.
So a Layer 4 load balancer works at the network level. All it sees are IP addresses and ports. The best analogy is a mail sorter who only looks at the zip code on an envelope. It doesn't know what's inside, it just knows where it's generally going. Because of this, it's incredibly fast. But a Layer 7 load balancer, it's much, much smarter. It works at the application level. This mail sorter can actually open the envelope and read the letter inside. It can inspect the URL, the headers, everything. This lets you do really intelligent routing, like sending all requests for /API/video to your powerful video processing servers and all requests for /images to your image servers. All right, let's dive into our final advanced topic for today. We're going to tackle a really common and tricky problem you run into with distributed systems. What do you do when a user needs to talk to the same exact server over and over again? This is what we call the sticky situation. And the solution is called session stickiness, or sometimes session persistence. It's a feature where you basically tell the load balancer, hey, see this user? For their entire visit, I want you to send every single one of their requests to the same server we send them to first. This is absolutely critical for things like a shopping cart. You don't want a user adding an item to their cart on server 1 and then on the next click get sent to server 2 where their cart is empty.
But, like everything in engineering, this introduces a major trade-off. We solve the shopping cart problem using cookies or that IP hash algorithm we talked about earlier, but we risk messing up our load balancing. What if one server gets stuck with a few really active users and becomes overloaded while other servers are just sitting there? The more modern and frankly more scalable way to solve this is to take that state, that shopping cart, and move it off the application servers entirely. You put it in a super fast, centralized cache like Redis that all of your servers can read from and write to.
And that really leaves us with the final question, because this is the exact kind of decision engineers have to make every single day. There's almost never one perfect answer. It's always about understanding the trade-offs. So for your next big project, what's it going to be? Will you go with the simple approach of sticky sessions? Or will you invest in the raw scalability of a shared cache? Something to think about. Thanks so much for joining me for this explainer.